couple announcements. This is a short course on quantum computing and quantum information. I want to make a couple of announcements here. First of all, this is being taped by the gentleman in the back of the room. Over a period of a couple of days, it will be translated to a DVD and made into a streaming media file. So this information should be accessible within a few days and then over a longer period of time after the class ends. The class is being put on basically for the people that are in the room here. It's being funded by an LDRD project, yet it seems to have just taken off in terms of its popularity, and there's a lot of people in here that are not associated with the LDRD. Now, Ivan is not going to charge extra to make the class, more technically sophisticated or less technically sophisticated. I don't really know what the specific interest of the audience is here and also at California. And what we're hoping to do is over the course of today and perhaps the next lecture, get some idea as to what the audience is looking for, and we can do some adjustment in the nature of the course based on that information here. There's a schedule that I sent out via email. We have reserved this room every Wednesday at this time between now and the end of the year. There are irreconcilable conflicts for some of the dates. We can continue to change that, and so if there's a consensus among the attendees that we should delete a date, we can move everything back by a week. Okay, subject to the availability of the speakers and so forth. I passed around in California, in New Mexico, a sign-up sheet. That's the list of the names that I got from people via email over the last month or so. If you could make sure that you've got a check mark next to your name, or if you're not on the list, please write your name in below. That's the only way I'll have to connect with you folks in the case that there's a schedule change. But I'd like to introduce Ivan Deutsch, who will give the short course today and for the next number of weeks. Ivan has a bachelor's from MIT, a PhD from Berkeley, and has been a professor at UNM for the last 10 years or so in the quantum computing area. And so, this is your job, putting on courses of this sort. So, Ivan, would you please begin?
Thanks very much. Well, very happy to be here and have this opportunity to basically have a discussion with you about this evolving and burgeoning and growing area of quantum information science. So this is a little bit of a challenge for me in terms of the audience, and as Eric said, this course hasn't yet been fully constructed, so that means I'm ready to get feedback from you as we go and tailor it more towards the directions that are of your needs. So in particular, one of the big challenges for me here is going to be taking the temperature of people's backgrounds and levels of sophistication that you're interested in learning about this material, and I'll do my best to adjust appropriately. I think one of the things that's most exciting and interesting about this field is that it's highly interdisciplinary. But at the same time, that means that it's a real challenge because the fact that many of us come from different disciplines means that we have different backgrounds and different languages that we speak. So I'm going to ask, as we go, to get your feedback, and I mean this really to be a conversation, so you should certainly be interrupting me as we go and asking any questions that you have. So I plan to construct a website over at UNM. As I should mention, I'm part of a bigger group at UNM that is an information physics group, mostly in quantum information, and you can visit us at info.phys.unm.edu. My group sub-page is there, and then I have a whole list of my classes. So I plan to distribute these lectures there for you to download. They'll either be as PowerPoint or PDF. Depends. Probably PDF, just because I find that since I use a Mac, it may be that some things are not compatible unless, but I'm a religious zealot, so what can I tell you? So this is the tentative syllabus. it's a little bit different from what Eric had distributed in terms of the ordering, because the intention is to have 1 or 2 guest lecturers come to give some of these presentations and discussions. In particular, I'm hoping to get Richard Hughes down from Los Alamos to give the presentation about quantum cryptography. And Richard said he wouldn't be able to do that until after Thanksgiving. So we're putting that at the end. At least that's the plan at the moment, okay? All right, so the first question here, I'm a physicist. My background is in quantum optics. And you may have heard that this year's Nobel Prize in Physics was given out in quantum optics theory. So those of us who are in the field are pretty excited about that. But now you might ask, well, why is a physicist talking about information or information theory? And it really goes to this mantra that those of us in the field like to chant, that information itself should be considered in a physical context. And our little scroll here, our mantra is that we really can't think of computation and information processing purely in the abstract, but we really should think about it in the context of the machines that are carrying out the computation. And the physical laws that govern those machines are going to constrain what the capabilities are of computation. So whether I'm trying to factor a number in my head, do it on Abacus or on my Mac Classic, I really need to think about what are the physical laws that govern the operations of those physical devices. The question of information in physics has not such a long history. You might say that really one of the first instances in which information played an important role in questions relating to physics and vice versa was in the famous Maxwell-Demon problem. Maxwell contemplated in a thought experiment whether or not one could violate the second law of thermodynamics if we had some kind of demon, as he thought about it, some creature which could observe the individual trajectories of molecules, and by seeing which ones were hot and which ones were cold, sort out those molecules and open up a little trap door and let only the hot molecules move into one chamber and the cold molecules, thanks Eric, move into another chamber, and make a system in which I can constantly develop a temperature gradient which I could then run an engine with and resort molecules and thereby decrease their entropy. And of course, it will require some kind of demon there to be able to observe what was going on. This problem had many resolutions, and close to a century later, Leo Szilard kind of distilled down the problem to thinking about, well, what would happen if I were able to just, through some intelligent being, here's Leo, trying to decide, well, look in a chamber and decide whether a particle was on one side or another, and then thereby establish a pressure gradient which could be used to do some work. So what Szilard's resolution to the Maxwell-Demon paradox was that the process of measurement by the intelligent being would require, in some way, some kind of physical process that would have that extra entropy increase within it. and that extra entropy increase would be related to this amount of work that would be done if I can decide whether the particle's on one side or the other and attach, this pulley the right way. So Szilard was really thinking about this idea of what are the actual physical limitations on measurement and how that physical limitation then impacts the ability to do a physical process. And this really sort of began a trend. The thermodynamics of computing was something that really took off in the latter part of the 20th century. And the resolution to the Maxwell-Demon really came in thinking about what were the ultimate limits, how much power is really necessary, what are the thermodynamic limitations to doing computation, where is the dissipation necessary to do computation, how much heat is really necessary to generate. In the same way we know that machines have a certain limit, there are only certain much efficiencies for which we can run machines, since that is to say steamboats, etc. How much heat is necessary to dissipate in doing computation? And Landauer really is really one of the fathers of this field, thought about this pretty hard and realized that there is a deep connection between whether a computation is logically reversible and whether it's thermodynamically reversible. And realize that the only truly irreversible step is erasure. That erasing a bit in your quantum memory, or sorry, in your memory, not your quantum memory, just your memory in your computer, would require some dissipation of energy. And Bennett then used that Landauer principle to resolve the Maxwell-Demon paradox to show that, in fact, it wasn't the measurement. The measurement could be done reversibly. But it was the fact that every time, if it was a closed system, every time Szilard has to decide whether it's on the left or right, if he doesn't have an infinite amount of memory, he's going to have to erase that memory. And it's that erasure that accounts for where the increase in entropy is in doing that work. So there has been this one trend that was going on at the latter part of the 20th century in understanding the thermodynamic limits, classical thermodynamic limits of computing. There's this mystery guy here, Paul Benioff, I couldn't find his photo on the web, who, in sort of contemporary with Bennett, thought about, well, reversible computing, quantum mechanics is reversible. We'll talk about that a little bit. And so one way one might implement a reversible computer is if it would work through the laws of quantum mechanics. But it was really, Benioff didn't really, at that point, understand the true power of quantum mechanics to do not only things reversibly, but at the same time, perhaps more powerfully than a standard computer would be able to carry out such a computation. Around the same time, Richard Feynman was thinking about how hard it was to solve quantum mechanics problems, simulate them on a classical computer. Now, there's a reason we'll talk about this a little bit, but it really has to do with the fact that the complexity of the quantum problem grows exponentially fast with the number of constituents. And Feynman sort of mused about this and said, well, somehow nature solves this problem for itself. And so perhaps if we had a machine that was governed by those microscopic laws of quantum mechanics, if it worked that way, it would be able to simulate other quantum systems. So what Feynman was really thinking about was quantum simulations. This guy Deutsch, no relation that I know of, David Deutsch from Oxford, took this idea really seriously and constructed what was really what one might consider the first real picture of what a universal quantum Turing machine, if you like. So right around there's this little corner in the mid-'80s where this idea of a quantum computer was really being born. But it wasn't something that I think a lot of us were paying a lot of attention to. It was something that was going on in some small corners of different fields of physics and information science, but not really quite mainstream science at this point. There's one other trend, of course, that we all know about that I think is partially behind why this field has become really interesting for many of us. And of course, that's Moore's law. And the fact is, it just doesn't take a genius to realize that eventually, as we shrink and shrink our feature sizes, we're going to start reaching the quantum limits. And I'd say when people were thinking about this, what comes to mind is that this is a real problem, that this is worrisome, that when we start getting to the microscopic level, quantum world is bad, because the quantum world we think about as there's the uncertainty principle, and so we don't know things as well, and therefore we're not going to be able to control it the way that we're able to control our classical currents moving in transistors. And so there really is, was, and I think continues to be in some sense a worry, but the message now that I want to bring here, and the message I think many of you have heard, is that really the quantum world opens up new opportunities to do things, opens up the door to do things in a completely different way. Okay, so we're talking about information here, but what is information? Probably many of you know this better than I, but from a physicist's perspective, it's a little bit puzzling to try to quantify this. So let's just think for a moment. So let's play just a little game. So do you have any guesses on this one? What about this one? Quiz show, right? Okay, so why is it that this one was really pretty easy to guess and this one is game show? Why is this one more difficult to guess? Right, this one's all vowels and this one's got a Q and a Z, and it's got a Q and a Z in a very particular place. So why is that? What we're using is our information. We're using our prior knowledge to make inferences about what is a message. And so information ultimately is about what we know. It's about us, about what we know. And we should be thinking about information in a context of probabilities. And really, I think the right way to think about that is from a Bayesian perspective, that I assign a probability to something, that message was quiz show, based on some prior information I know about the English alphabet and vocabulary, for example. So we have these conditional probabilities that we assign to our everyday choices based on our prior information. Now, the theory of probability is really the theory of logic. So, for example, if I wanted to ask what's the probability that the message was X, irrespective of what I know, well, I would kind of average over all the different possibilities. I would say, well, there's a probability that it's X given that it's Y, 1 times the probability that is Y1. That's one alternative. Another alternative might be Y2. So there's some probability that it's x given it's y2 times the probability that it's y2. These are different alternatives, y1 and y2, and I want to know the probability of x irrespective of the two alternatives. There's another thing we do, of course, when we gain new information, we change the probabilities that we assign to those to those outcomes. So if I started with some initial prior, this one's losing its juice. There we go. If I had some initial prior information y1 and I learned a new piece of information y2, and I wanted to then update my initial prior assignment, Bayes' rule tells me how to do that. Bayes' rule tells me that, well, I should relate my updated probability to my prior probability. It's related to some normalization and a likelihood that I will get this new piece of information given my initial information. Excuse me. We got to switch out here.
Just this. Audience is so quiet.
I know. I'll have to shake them up. Everyone needs coffee.
We're done.
Okay. All right. So that's the very, very basics of how we should be thinking about information. So now the big question, and the question that we'll be spending, some time here discussing, and I really do hope that you'll interrupt me here to give me a sense of where you guys are at with relation to this. Because for some of you, I know what I'm going to discuss is going to be what you learned as sophomores in physics class, and for some, maybe you've never seen it before. So the question is, in what ways does the quantum world differ? How is the information and inferences that we make in the quantum world different from the information and inferences that we make kind of logically? So here's the canonical paradigm. So here's just a little picture of an optical kind of, we love quantum optics. So here's my single photon source. You can think about it if you want as just a laser that's been highly, highly attenuated so that in some time slice I'm going to detect, there's very low probability of getting any more than one photon. And it's incident on a half-silvered mirror, a 50-50 beam splitter. Okay? Now, if this was just a classical wave, light wave, a light beam, then 50% of the intensity, say, would be transmitted, and 50% of the intensity would be reflected. Okay? That's a 50-50 beam splitter. The quantum world is a little bit different. When a single photon is incident on this beam splitter, what happens is either this detector A goes click, and that happens with the probability of 1/2 if this is a 50-50 beam splitter, or this detector goes click, and that happens with a 50% probability. So it's kind of a Geiger counter. There's a kind of random process where the photon is either reflected and clicks here, or the photon is transmitted and is clicked there. We never see clicks simultaneously if this is a single photon source. As I say, if I were to put a coincidence counter between them, I would see 0 coincidences. I only see a click here or here. That kind of experiment has been done, by the way. Okay, so now, if that was it, big deal. Probabilistic, I flip a coin, 50-50 chance I get a click one place or the other. Quantum world isn't quite that simple, not even close. So now instead of, I have my 50-50 beam splitter, as we said before, and I have if this was a classical field, we said that part of the intensity would be here and part would here. So what I'm going to do is I'm going to recombine these two paths into an interferometer, take the path here, put it on, so there's one path, path 1, put it on a beam splitter. There's another path, path 2, recombine them. If I align these paths so that they're exactly equal in length, then what I find is that with 100% probability, this detector goes click. And with 0% probability, do I get a click in that detector? Okay? So, now, maybe that's not so crazy if you think about light waves. I mean, yeah, I get interference between different waves, and I get constructive interference along this path and complete destructive interference along that path. But these weren't just waves. I mean, let's think about this logically. Okay? We said we should use probabilities to assign to different possibilities and then ask, what is the probability for certain outcome? So there were two alternatives. At the first beam splitter, the photon could have, so we said, you know, that when we put a detector here or here, we never got a detection in both paths, right? We only saw a detection in path 1 or path 2. We never saw a detection in both paths. So in some sense, the photon takes either path 1 or path 2, right? So there's some probability that detector A clicks, given that it went through path 1, times the probability that it actually went through path 1. That's one part of the probability that A clicks. There's another way A can click, right? A can click if it takes path 2 and then it gets transmitted. Okay, so I should add that to that. Those are the two alternatives. So if I just do, you know, the most trivial probability theory I would say the probability that I should get a detection in A is a half, not 1. How could it possibly be 1? That's illogical. But the quantum world has its own logic. The way in which we have learned to assign probabilities or make predictions about events has its own calculus to it. A calculus that defies classical logic. I mean, after all, we said probability was just logic. And this is what makes it so challenging because, you know, how in the world are we going to do something if we can't use logic? So we have to develop a new intuition in order to be able to make predictions about what happens in the quantum world. So what we're taught, what we learn, and what we see works well in experiment is that what we do is we think about what I call a process, like transmission through a beam splitter or reflection from a beam splitter of a photon. And to each of those processes, I'm going to associate a complex number, a number with a real and imaginary part. And that complex number we call a complex amplitude, our famous psi. And then the rule is that I calculate the probability of observing that process as taking the square modulus of that complex number, okay? Multiplying that number by its complex conjugate. That's a real number. If these are normalized appropriately, it's a number between 0 and 1. I'm sorry, that should be an event. I'm sorry, yeah. Typo there. Yes. Okay, so that's the rule. So what does that imply now? Okay, so one way, I think sort of the clearest way to understand how quantum mechanics, how to apply these rules is what I call Feynman's rule. He stated it this way. If I have a set of indistinguishable processes, that means there's no measurement that's been done that's distinguished them, and there's no way, there's nothing hiding in the world that can tell me which process happened. Then what I should do is I should add not the probabilities as we did in the previous example, but instead I have to add the amplitudes, these complex amplitudes associated with those processes. So for example, what does that mean? Here is the rewritten amplitude associated with the process of the photon hitting detector A. But now what I'm doing is instead of with probabilities, I'm working with these complex numbers. So here's an amplitude for the photon to hit the beam splitter having gone through path path 1, times the amplitude for the fact that it went through path 1. And here's the amplitude for it to hit detector A having gone through path 2 times the amplitude for going on path 2. So now the rule is if I want to find the probability for detector A to click, what I have to do is I have to take the square modulus of that complex number. Okay, so I have to do that. So let's do it. Take this, multiply it by its complex conjugate. So the first term here is this times this complex conjugate and this times its complex conjugate.
Don't you really have 4 paths?
I do. 4 paths.
Back in your little model with the splitters and the mirrors? Not the day.
Yeah, there is another amplitude for it to hit B.
Right.
And that would be its. This is just what is the amplitude associated with the photon hitting detector A. So, but there are 4 terms in this multiplication of these complex numbers. This times it and the so-called cross terms. So if we look at what these things are, this can be replaced by the probability. Let's go back again. We see each one of these guys is the square of an amplitude, and each amplitude represents a process. So there's some probability for A to go click given path 1, and that was related to the square of that amplitude, etc. So what I see here, if you look pretty, it's not so hard to see, that the first term here is what we got from just classical logic. While the second term here is something weird. The second term here is interference, but it's quantum interference because it's the interference of processes, clicks, of things that go bang. These are events. This is not continuous waves. This is detectors, Geiger counters. What's the probability for them to do something? And what we're saying is that when I want to calculate that probability, I can't just use my classical logic. I have, in addition, other possible terms. And these terms can either add or subtract to this to make this, for example, 1, when the classical thing we said was a half. So that's the key point here. Does anybody have any questions about that? Yes, sir.
So is there a way of interpreting, a physical way of interpreting the phase of this complex number? So its amplitude is the probability or the squared amplitude. But how do you interpret the phase?
There is no interpretation of the phase per se. the best I can do for you is to say a probability, classically, is an assignment we make as a number to make some prediction about the outcome of an event. In quantum mechanics, the wave function or the complex amplitude is an assignment we make in order to make a prediction. And it's a good question. So what is the wave function? Is the wave function a wave, like a water wave, or even something as abstract as an electromagnetic wave? I think the best answer to that is no. The wave function is a figment of our imagination. The wave function is what we assign to describe the system. In the same way that probabilities are not physical things, they're things we assign based on our prior information. It's just that the way in which we do it, the calculus that we use to make those predictions, is the born rule. Yes, sir. Oh no, you want to have a follow-up and then?
Yeah, I was just so you would assign from some experimental observations the probability and the phase.
Right. So we know, and we'll talk about this much more next time, sort of the rules of how you assign the whole complex number to a given experimental situation. So that would be based on a preparation procedure, so your initial condition, and then some notion of dynamics of how we should, in the context of physics, how the wave function evolves. Yes.
So my question is, our probability calculus is derived as sort of infinitesimal limit of a discrete theory, based on, let's say, combinatorics. So is
Based
there...
on, sorry?
I'm saying that our probability calculus is derived infinitesimally as limit of combinatorial theory.
Uh-huh.
So is there a discrete version, or let's say discrete realization of this thing in the green box? The classical logic, I can always think of it as probability is a coin toss.
Yep.
What is the discrete version of the thing in the green box?
Well, here too, we will have sort of the equivalent of a coin toss, but instead of a bit of the two outcome, we're going to have a quantum bit. We're going to have a qubit, as we'll call it. And ultimately, the degree to which I can't say I know enough about what you might call axiomatic quantum theory. People are trying pretty hard now to think about what's an appropriate set of axioms from which what's a minimal set of assumptions for which I need to use in order to derive quantum logic. And it's an interesting mix of physics and information theory that's being used to derive that. As the physics of this came really not axiomatically. It just came from seeing some weird effects in the lab and then trying to come up, this kind of calculus, if you like, or this kind of mathematics that assigns, well, there's some complex amplitude and then the square of that amplitude, came from wave theory, right? In wave theory, we have an amplitude and an intensity. And the relationship between the beam splitter picture, which I said some fraction of the intensity was saying, well, okay, I'm going to associate the fraction of the intensity with the probability for the photon to do that. And it sort of built up that way. But now that we sort of have rules that have worked for 100 years pretty well, trying to step back and say, well, what are the real axioms and where does this come from? And what part of it is really physics per se, physics in the sense of, the objective laws of nature versus what is really kind of the way in which we learn about nature and the informational aspects of it. So I don't know if that really answers your question more about the discrete, but okay. Yeah. So we'll come back more to the qubit. Okay, great. Please do interrupt me. Okay. Now, all right, you say, come on, Deutsch. You just told me that the photon, when it went to the beam splitter, it either went one path or the other because you put a detector there. You never saw two clicks, right? That the photon either clicked in one detector or another. So I'm going to fool you. I'm going to put here now a new kind of detector in one path of the interferometer. This is going to be some, what we call a quantum non-demolition device. It's a transparent medium, but maybe has some kind of electro-optic effect. That when the photon is transmitted through this crystal, a voltage will develop across the crystal. And I'm going to look for a voltage blip. And I'm going to watch to see the photon, whether it went this path or that path. Okay? I can set that up. Why not? And then I'll know that if it went this path, I can tell you both, it only goes, we know without this detection, we know only this detector goes click, never this one. So I'm going to defy your quantum mechanics and show you that I can follow this trajectory around. So if you do that, unfortunately, or fortunately, depending on how you look at it, things change. If I get a detection here, instantly, I know that the photon went on this path. And that, in that case, I get a 50-50 probability. Them's the facts. I don't actually need to watch this thing go. It doesn't. It's like my consciousness needs to be there to watch that. People get confused about that all the time. It's just the very existence of this interaction changes the possible processes that could have happened. And since this is the only process consistent with this voltage lighting up, I must then collapse the wave function such that the photon goes through this path, and then when the photon hits this beam splitter, it has a 50-50 chance of hitting one of these detectors. So the process of putting this transparent crystal in here will allow this detector to flash. Very strange thing. So this, again, this goes through many different names. As we said, this is what we sometimes call the collapse of the wave function. This is related to what we call wave-particle duality. The interference effect that allowed that when I set up this interferometer such that all the intensity went this way was a wave effect. But if I try to see that the photon really has a particle-like property, that it is only one place or the other, then it has particle-like behavior. It doesn't have wave-like behavior. And it has this random transmission reflection. Bohr, who was really the great founder of quantum ideas, called this complementarity, that you can only see that the photon is both particle and waves and has complementary aspects, wave and particle. You cannot really see them both in one experiment. You had a question?
Yeah, I was just curious if you set up that apparatus and replace the single photon source with the source of continuous photons, and you had the detector there, would the interference actually of the waves go away? Because we have multiple photons. I mean, there actually is a wave pattern, correct?
Right. Well, so if I suppose I took a laser beam and I did this experiment, the detector has some integration time for which it integrates, and then it decides, okay, it's gonna then make a detection. So then there's a question of whether in that integration time there's certain intensity. How many photons are there? So if I have multiple photons in the packet, then it gets a little more complicated. I have to then think about the statistics of, well, how many photons are in that packet? I have to then, I would add over all the different photons, and they would add in a kind of averaging way. So I wouldn't see this effect so well. On the other hand, if I had the same continuous light field, and I turned down the intensity, I put a large attenuator in front of my laser beam, such that in the integration time of the detectors, there's very low probability of me getting any more than one photon. Most of the time I get nothing. But every once in a while I'll get something. So even though it's a continuous light field, that light field is made up of, in some sense, a train of discrete photons. I would see this effect. So it really depends upon, the light field itself fundamentally has one description. It's a quantum state. That quantum state has both wave and particle properties. Yes?
What happens if you put detectors in both spots?
You would still get 50% in each, because what would happen is either I would have a picture that looked like this, or I would have a picture that looked like this, where the photon took path 2. If I saw this light bulb go off, or whatever, this voltage, then I would know this is the path it took. And then when the photon takes that path, it has a 50-50 chance. But those two paths are distinguishable. Remember, Feynman's rule said, add the amplitudes if the processes are in principle indistinguishable. But the fact that I have the detector in the path makes them distinguishable. And if they're distinguishable, I add probabilities, not probability amplitudes. Yes?
All right, what if you have that apparatus and the photon you send out doesn't go through the detector? Because you have the apparatus there, you know that it went through path, I guess you're calling it 2.
Yeah.
Is
You mean this one? Yeah. This one.
The one that's not shown in
Okay,
the
that's
slide,
2. Yep.
The other one. So the apparatus did not go off.
Yep.
At the same time, conceptually as an observer, you know that it must have went through path 2. Now, does it still always go to detector A because it didn't pass through the detector? I mean, you actually made the measurement implicitly, but at the same time, is that the photon would have went through the same path regardless of what the detector was there. So the question is that if you actually did the experiment,
That's right.
what would happen?
You're absolutely right. It would do that. And that's called interaction-free measurement. By just the fact there's some probability if that the photon, in the Gedanken experiment you're thinking about was I put some kind of explosive in one arm, and then I put in this interferometer. It's a perfectly absorbing explosive, and it absorbs one photon, it'll blow up. But now I put that in one arm of the interferometer. 50% of the time, the explosive won't go off, but I'll know it's there because this detector went click. That experiment's been done, not with an explosive, but the equivalent thereof.
But when the ones that take with the path, which ones, one of which was?
Yeah, this one's one.
Yeah, the ones that take path 2 that aren't observed, correct? Do they all end up in A?
No, 50% of the time they do, because we have, as was just,
Observe one side.
we just know, we've done implicitly a measurement that knows that since this thing didn't go off, it was in path 1, so we update our state of knowledge. We know the photon went in that path. But we don't even have to know it, it's just that it's the existence thereof, of that interaction that matters.
So if you just put the crystal there, but you didn't actually have the volt detector,
Right. I mean, what would have to happen, there needs to be a voltage established. It needs to be something that, in principle, it's not just this metaphysics. There's actually something developing, a voltage developing, some electrons moving in the crystal, even if I don't put the voltage meter there. But it's that physical interaction that matters. So it's the interaction with the other degrees of freedom of the world that change the physics of it, and therefore what happens. Yes?
So then is that true also for the actual detectors, the endpoint detectors? If they were not there, does that perturbate the system as well and change the result?
Well, I mean, they in some sense would affect what happens, you know, downstream. There's always causality. So it's hard to, it's not that, you know, the existence of these detectors here doesn't affect, how shall I put it?
You can say no.
You know, there's an important point here, which is that, and this is sort of one of the things I want to emphasize here, that new students of quantum mechanics always struggle with, which is what is, in some sense, real, and what is, or objective, and what is, I just have to leave in quantum limbo land. Ultimately, what quantum mechanics is a theory of predictions of outcomes of measurements. Ultimately, that's what it is. So what the question you have to has to be rephrased in a somewhat more precise way, which is, does the existence of these detectors affect the outcome of some other measurement? And we have to think what measurement we're talking about to then ask that question. So here, I mean, they're at the end of they've absorbed the photons, they're gone at that point. So you have to phrase your question in the context of what measurement would it affect. So the existence of, say, this detector here does not affect whether or not this photon with this detector will go click.
Still go click 50% of the
That's right. These are, of course, you know, these kind of puzzles that there's a whole host of them in quantum mechanics that, in fact, you know, there's a famous set of debates that Einstein and Bohr had where they grappled with what was really possible in quantum theory by just this kind of mind game and really struggling to get at its essence in that way. Okay, so now the question is, what the heck is collapsing? And this comes to the question of what is the wave function. So suppose I give you a promise, I put a coin in this box, and the coin is sitting there, either heads up or tails up. And I ask you, what is the probability the coin is heads up? Well, you know, I'm not telling you much. I'm telling you nothing except that there's a coin and it's got two sides to it. So given that you know almost nothing, you would assign equal probability to both. You would assign a probability 1/2 to that event. Now I open the box for you, and you see that it's heads up. Now I ask you, what is the probability that's heads up? You better say 1, otherwise I have a bridge to sell you in Brooklyn. So what happened? You updated your probability conditioned on the information you learned. Nothing changed about the coin. It's just what you learned about the coin that changed, right? So the coin was in this state of up or down. I don't know whether it's heads up or tails up. And in my mind, I didn't know which one, but then I saw it, and now I know. So my state of knowledge collapsed. So, okay, well, that sounds good. Maybe that's exactly the same way I should think about quantum mechanics. Kinda. So this comes to the question is the randomness that we see in quantum mechanics just that? There is hidden information, like the coin in the box. I didn't know what it was, but in principle it was knowable. And once I learned it, then I changed what I knew about it. So Einstein, was insisting really that this was the way things were. In classical probability theory, what we're basically saying is that we have an incomplete state of knowledge, but in principle it can be completed. I could know whether the coin is heads up or tails up. And once I discover that hidden information, I update my probability. And when I'm learning that hidden information is objective, a realistic property of something. And that's what Einstein was insisting, that quantum mechanics had to be like that. I mean, we had statistical physics before quantum mechanics, thermodynamics, and it was all based on a theory of statistics, that there were particles, atoms with trajectories. We just didn't have enough precision information like our Maxwell demon to know all those trajectories, and that's all that's going on. Things are random, only they appear so just because we don't have all of the information. Yes?
So I agree that with the box we have hidden information, but when you do a coin toss, where's the hidden information in that case?
The information is exactly how I threw the coin, what the air pressure was. If you knew all of that and it follows Newton's laws, then I can predict it exactly. So there's hidden information there. What the initial conditions are, what all the forces that are applied. Okay. However, quantum mechanics just ain't like that. It just is not. And we'll talk about this more. The main purpose of this lecture is to kind of introduce you to some ideas. But in the 60s, John Bell came up with a proposal for an experiment that has been performed numerous times now that shows that, in fact, there is no way I should associate a realistic property to a quantum particle that resides locally with that particle. If I want to assign objective realistic properties that I just discover when I measure them, just like the coin actually was always heads up, but I didn't know it, and I discovered it when I opened the box. If I want to do the same thing with the path, which path did the photon take? It's not going to work. If I want to make such an assignment of a realistic property that I just discover, then that has experimental consequences. And those experiments just are not consistent with that kind of assignment. I'm not saying this completely clearly because I have to give you real examples of that. And that takes a little more. We'll want to spend a whole lecture on that. And that's related to this whole craziness of so-called entangled states. Entangled states are, in some sense, the non-classical feature, something that has no analog in the classical world. So we'll talk about that in a couple of lectures. So what we've learned is, there's a weird quantum world out there which has interference between indistinguishable processes. It's got this uncertainty, which we really haven't talked about, but we will, between so-called incompatible observables. There's this kind of fundamental trade-off between what I learn about the system and how much I disturb the system, an information gain measurement disturbance trade-off, and then we have this business about entanglement. And the whole business of quantum information theory is basically, putting this weirdness to work somehow. that, you know, for generations, we've known that quantum mechanics is weird. And, you know, one of the things that physics students are often faced with is being beaten up by their professors to say, don't think about this. If you're a real man, you'll just use quantum mechanics. You know? I think that's garbage. And I think we're now understanding, you know, if there are if things were obvious, I mean, special relativity is weird too, right? But we don't have the same kind of constant, oh, what does it really mean? You know, there are a few paradoxes. You learn about the barn and the contracting ladder and the twins and all of that, but you understand how it works. The problem with quantum mechanics is we still don't really, I mean, no local realism. What am I talking about if things aren't locally realistic? What am I measuring? And what the whole process of really trying to delve in and understand the nature of what this new kind of logic means has now opened doors. We realize it's not just something for, you know, philosophers, that what it is now a new way of making inferences. Because what we said was information was about what we know, and using our predictive laws to learn new things. And because quantum mechanics satisfies a new kind of logic, that new kind of logic could be put to work. And that's what quantum information science is about. So, what's it good for? Well, we're not so sure yet. I don't know. Maybe nothing will be the answer. Well, probably. But we're working on it. But let me just give you, you know, sort of there at the top of the food chain is this whole holy grail of a quantum computer. Quantum computation is certainly one important component of quantum information science. And, you know, the dream machine is this universal quantum computer that could carry out an arbitrary algorithm. Right now, the biggie is Shor's algorithm, which I'm sure many of you have heard of, to be able to factor primes efficiently. Sort of in the same genre is Feynman's living out Feynman's dream of the quantum simulator. So maybe it's not a universal quantum computer, but it can do some small class of problems like simulating models that predict high temperature superconductivity and seeing if they really do give us that. But we can't solve them on any reasonable cluster or supercomputer. Quantum cryptography is perhaps the most mature area of quantum information science. As we saw, there is this sort of irreducible information gain disturbance. So, you know, you can imagine that it would be an easy way to detect for eavesdroppers. And that's really what one's relying on in QKD, a number of those weird quantum features, incompatible measurements, irreducible disturbance due to measurement, etc. So those weird properties are put to work there. Quantum communications is another sub-area. We might ask, if I have some channel I want to communicate with, what is its capacity for information if that information is encoded quantumly versus classically? Does it change? What if I have these distributed parties and they want to do some distributed computation? How much information classically do they need to share if, in addition to those classical channels, I give them quantum resources? This entanglement, this non-local something or other to do so. And sort of, you know, lurking there close by is the problem of sensing and metrology. You know, metrology is really a distinguishing problem, understanding one situation from another, distinguishing states. And to be able to do that with ultra-high precision, quantum information gives us some clues how we might improve the limits of metrology. an area of great interest to me. Okay, so let me just end soon with just a very, very brief overview here of hardware and software. So we had the basic ideas. So what's a quantum computer say? Well, let's think first of all, this comes to the question that was raised earlier about the discrete quantum systems. When we think about information, we think about digital logic, right? So our fundamental unit of information is the bit. And the bit is just two pretty distinguishable states, all right, to the degree that I can really, with good confidence, say it's either this or it's that. Well, however I want to encode that. The analog in the quantum world is what we call a quantum bit, or a qubit. And everyone complains that it's QU and not Q-bit or qubit, but we're stuck with this. So what is a qubit? Well, a qubit is a quantum system that has two what we call orthogonal states. Orthogonal states are the quantum exact description of two states that are perfectly distinguishable. Remember, in the classical world, we had to know zero voltage from whatever the voltage is for a bit in a transistor. They have to be distinguishable. Quantum states are generally not distinguishable unless they are, quote unquote, orthogonal, and we'll get to that next time, what that means. But those two states have to exist in this limbo land. We have to be able to produce them in superposition, like the two paths of the photon in the interferometer. So lots of examples of a qubit, just like we can encode a classical bit in many physical systems. A qubit could be encoded in many physical systems, and many are being considered to be the carriers of quantum information, photons, photonics, whether they be the paths in interferometer or the polarizations of light, whether it's vertical or horizontal. They're orthogonal and therefore distinguishable. I can think about encoding a qubit in energy levels of an atom and the degree to which I could read out or manipulate individual atoms or ions. The so-called spin of an electron. An electron is like a spinning top. It has orientations. In fact, it only has, when measured, it only has two orientations and thus acts as a qubit. We can think about charge states in semiconductors, and people do. Or the mesoscopic currents in a squid. All of those are being explored in the laboratory as carriers of quantum information. So the language we use here is we assign this little symbol here is called a ket. We'll talk about that more next time. A so-called logical basis. This language of orthogonal and basis obviously harks back to linear algebra, and that's a whole lecture in itself, which will be next time to remind you of that and teach you how that's related to quantum mechanics. So I have two states, distinguishable states, which I label logical 0 and logical 1, just like a bit. And 0 could be the photon went through port A of the interferometer, and 1, it went through port B of the interferometer. The key here is that the qubit can exist in a superposition. So here, again, I'm adding amplitudes. C0 and C1 are meant to be complex amplitudes, the square of which represents the probability that I'll measure the qubit in 0. The square of C1 represents the probability that I'll measure the qubit in state 1, 0 or 1. However, it's not either or, it's both, because it's in superposition. Just like the photon wasn't really in one path or the other, in some sense it was in both, because once I found it in one path or the other, it was a different beast. So in order to do computation, for example, I need to be able to transform my bits. I need to do Boolean logic. So classically, we know that I can do Boolean logic by just a series of logic gates. And there's some set that are universal. When I think about a single bit, there's only two things I can do to it. Nothing or flip it. Nothing else you could do to a bit. A quantum bit is a different beast. I could do not. I could flip 0 to 1 and 1 to 0. But then there's other kinds of transformations that just don't exist in the classical world. I have the square root of naught. So the square root of naught takes 0 into some superposition of 0 and 1. I here is, the complex square root of -1. So in some sense, the quantum algebra is kind of like from real numbers to complex numbers. Certain things just don't exist in the real numbers. And this kind of operation is like the square root of -1, right? It doesn't exist in real algebra. We need a new kind of algebra. But that new algebra kind of moves us into the complex plane, allows us to do computation. Anyone who's ever done a contour integral maybe that remembers, that it's actually easier than sometimes doing if you can go into the complex plane. And similarly here, the fact that I can move out of this constraint of either 0 or 1, but I can be in limbo land of both 0 and 1 allows me to sort of move through the logical space more efficiently, we hope.
So is the idea of square root of naught that if you apply square root of naught to the output of the square root of naught,
You get naught, exactly. And you can try that. Just use this twice, and you'll see that it does not. It does not. And then, but what's crucial here is that the square root of naught has these eyes here. I mean, there are other kinds of transformations. For example, what's known as the Hadamard, which looks quite similar to this. The only difference is here I don't have the eyes, and I have different signs. But notice in this guy, after the transformation, the probability that I'm in 0 is 1/2, and the probability I'm 1 is 1/2. How do I know that? Well, the coefficient out front of this is 1 over square root of 2. So I square that, I get 1/2. The coefficient in front of this is -I over square root of 2. Take the absolute square of that. That's also 1/2. So in both of these guys, there's a 50-50 probability that if I look at the qubit and ask, are you 0 or 1, it's like a random coin. And same thing here. But this is a very different state than this. In fact, if you do H twice, you get the identity. Whereas here, you get not. So those phases matter. I forgot who asked the question about the phase, but those phases matter, and those phases are determined by the dynamics, the equivalent of Newton's laws, tell us how the phases change. Now, suppose I have a bunch of qubits. Say I have 3. Well, if I have 3 qubits, classically 3 qubits represents, or 3 bits, I'd have 8 alternatives. Okay, so this is 0 through 7 written in binary. So quantum mechanically, I have 7 different quantum registers, 7 different possible states in which I can measure. If I were to measure each qubit and ask, are you 0 or 1, and then accumulate those digits together, I'd get 7 possibilities. However, what's different here, in the same way that for the single qubit, I could take a superposition of the logical states and form a state that was neither 0 nor 1, but somewhere in between 0 and 1. In the multi-qubit register, say for 3 qubits, I can take a superposition of 0 through 7 and have 7 different alternatives all existing simultaneously. And in fact, if I had n qubits, I'd have 2 to the n different alternatives, which can exist in some sense simultaneously. That kind of state, so one thing to note is that the space grows exponentially fast. And that's an important aspect. Of course, that's true classically too, right? I mean, of n bits, I have 2 to the n different registers. But the point here is that they can exist in superposition. I can, in some sense, have all of those possibilities exist simultaneously, whereas in the classical world, it's one of those alternatives at once. So this kind of state where I have superposition is an example of an entangled state. Well, that is it. We'll talk about that more. Yes?
When you take that linear combination, the C sub x, those are between 0 and 1 and sum to 1?
They are complex numbers whose square modulus is between 0 and 1 and square root to 1, because the square of this amplitude tells me the probability of getting x. But they themselves are complex numbers. So this idea then leads us to this picture of, what is a quantum algorithm? Well, a quantum algorithm is a map that takes my input state, say for 3 qubits, and maps it to an output state with some map, which I'm calling here U hat. It's really a unitary matrix. We'll come to that next time. So the idea here is that suppose I want, there's some database search, and I want to know, it's 0 through 7. I don't know which one it is. I'm searching my database. So what I do is I create a superposition state of 0 through 7 and send that as the input state to my computer, which performs this algorithm. And then what the algorithm has to do is somehow interfere these 7 different alternatives in such a way that the answer gets constructively interfered and the non-answers get destructively interfered. So that when I make a measurement with very high probability, I get the answer. Right?
So that's what the big ball is.
That's the probability.
One more or
Yeah.
less.
Yeah, that's it's piling up. All the probability is piling up there.
So why are there a few small dots?
Well, okay, and good question, because that's not a perfect algorithm. So the algorithm doesn't, occasionally you get that, but what you'd have to do is run it a few times and then collect statistics. But you hope that the number of times that you have to run it does not grow exponentially with the number of qubits.
Right. Otherwise, you might as well just use normal.
Exactly. So the whole challenge, it's not enough to just say, well, I should say, so this idea has been called, quantum parallelism. It's sometimes a parallel computer in the sense that it runs on all the possible inputs simultaneously, but with one device. However, that's not quite enough because the algorithm has to do the right thing. In the end, if the algorithm doesn't pile up the probability amplitude enough in the right answer, then when you measure it, you're not necessarily going to get the right answer. If I measured this, I'm going to get 0 through 7 with equal probability. Okay. Now, with all good things come bad. Quantum computing has all this promise, the promise of quantum information, but it in some sense has an intrinsic conflict to make it realizable in the laboratory. And that intrinsic conflict comes from the following. In order to do this quantum logic, I need to be able to drive the algorithm somehow. There needs to be something that's making the algorithm go forward. And you need to be able to couple to your qubits, and you need to do that with some kind of control fields. And this process of keeping the phases proper, because we said the phase of those complex numbers was truly important, is what we call coherence in wave theory. So I need coherent operations. But at the same time, because my systems, my qubits are coupling strong to one another, and they're coupling strongly to my control field, chances are that's not all they're coupling strongly to. And if they're coupling strongly to other things, well, that could be bad. As we saw, the other things can act like that voltmeter, which collapsed the wave function. And that coupling to the environment gets rid of the coherence. It's what we call decoherence. So the challenge in implementing this in the laboratory, the kind of engineering challenge we have, is how do we design systems which can strongly couple to one another and strongly couple to your control fields without strongly coupling to anything else? Because the quantum states, in some sense, are delicate and can quickly decohere. All right, so that's what I have for today. Meant to be just sort of the broad introduction to the ideas. I think I have on the sign-up list everyone's email. So I'll send out a message to everyone this afternoon just to have you touch base. And if you wanted to email me back with just a little bit about your background, so that will help me to understand how to tailor these. My intention next time is to talk about the basic formal structure of quantum mechanics, which will be necessary to develop this calculus that we've been discussing. So it's going to talk some about linear algebra and the relationship between that and the quantum states, etc. So we'll have a little discussion over email perhaps, and that will help me to tailor these appropriately.
Could I add, I'll stand near your microphone. I think there's probably about 10 people in here that haven't signed the sign-up list. So can I launch this into the room here? Could you pass it around, get your name on there? And also with the folks at Sandia, California, could you collect your emails and send them to me, and we can get you connected up with Ivan? Okay?
Great.
Also that letter.
Thank you.
Any questions over there in California? Not that I look over my shoulder helps you to hear me, but sorry, I have no sense of direction. Anybody else have any more questions? All right, great.